Welcome to today's lecture. We will start again as usual. Our practice is by recapitulating what we discussed in the last lecture, namely work done in different thermodynamical processes. So, we talked about isothermal process, isobaric process, isochronic process, and most complicated of all is the adiabatic process. So, different thermodynamical processes which I am going to discuss now again, just to emphasize the physical aspect of the calculations I did in the last lecture. Well, all these processes I will be talking about are quasi-static processes. I repeatedly told you what do I mean by a quasi-static process. That means changes are infinitesimal small. I make very small change in my thermodynamic variables, so that the system can always be thought to be in equilibrium. So, I will be considering ideal gas. For every instant of time, I can write PV is equal to nRT if I consider n moles of ideal gas. If not otherwise mentioned, I will be considering monoatomic ideal gas. Okay? So, I will consider different quasi-static thermodynamic processes and my working substance is an ideal gas, and we will verify, or rather we will use first law of thermodynamics, namely the conservation of energy, to justify different situation, whether there is a change in internal energy, whether heat absorbed or heat released. These are the things I am going to do in coming 20-25 minutes before I do the adiabatic process at some length. Okay? So, first process which we are going to discuss is very simple isothermal process. By the way, we have done mathematics in gory details in the previous lecture. So, today I will just quote the results. So, isothermal process is temperature fixed. Well, temperature remains fixed if I can draw a PV diagram. This is my pressure, this is my volume, this is an isothermal process. That means temperature constant, which immediately implies that Pi Vi is Ci. This subscript I, this denotes I am talking about an isothermal process. This is very, very important. It is not the initial value, it depends on the process. Okay? So, this is an isothermal process. Pi Vi is equal to Ci, which is equal to nRT. T is a constant. So, this nRT is a constant which is denoted here by Ci. So, in an isothermal process, I am going from P1 V1T to P2 V2T. Okay? I can think of this is an isothermal process in which I go from P1 V1 to P2 V2. Obviously, here you can see that V2 is greater than V1, which immediately implies that P1 is greater than P2. Okay? So, I am increasing pressure, volume decreases, and this I am going from high pressure to low pressure, okay? And this I will often call as expansion. Okay? So, isothermal process, temperature remains fixed, internal energy does not change, but pressure and volume change. I am talking about ideal gas. Internal energy is a function of temperature, and since temperature is kept fixed in an isothermal process, internal energy does not change. Okay? But pressure and volume do change. We calculated the work done. The calculated work done is PdV, which is nothing but if you go back to the previous slide, we are calculating the area under this curve, as I said in the very beginning of this set, and this work done can be easily calculated, which is nRT log V2 by V1. This is the final expression for work done in an isothermal process. If I consider expansion, that means V2 is greater than V1, which is the picture I have shown here, you can immediately see work done is positive, which is this one. Okay? What does it mean? Let us recall first law. These I will keep writing again and again almost in every slide. Okay? This is my first law or conservation of energy. I have said du is equal to 0 in this process. So, delta Q is equal to delta W. Work done is positive, that means delta Q is also positive, which implies system absorbs heat and converts to work. Okay? This is expansion, isothermal expansion, in which work done is positive, system absorbs heat and converts it to work. Now, if I think of contraction, what do we mean by contraction? Contraction is V1 is greater than V2, work done is negative, that means I am doing work on the system. Okay? Work is done on the system and heat. So, delta Q is negative, delta W is negative and system releases heat. It does not absorb heat. Remember, our convention was whenever system absorbs heat, okay, then delta Q is positive and system does some work, delta W is positive. Here, work is done on the system because work done is negative. As a result, system releases heat. These things will be very, very important when we go to engine and refrigerator. Those things have multiple thermodynamic processes. So, we have to be careful about the sign convention and we should know when heat is absorbed or when heat is released. Okay. Now, proceed. We can do this isothermal process calculation in an alternative way, which is the same result. You know PV, this is the thing we are calculating, PdV. And how do you get PdV? I just use this equation, PV is equal to nRT. Okay? Just to tell you something interesting mathematically, let us try to see what is V. V is nothing but nRT over P. So, what is change in V dV, which is nothing but I am doing a differentiation nRT over P square dP. I put it back in this equation. I want to calculate the work done, I put it back in this equation, I get nRT. Now, integral is not over dV, I want to write it in terms of dP. So, I will be having a P down by a factor of P square, which I get from here, and then dP. So, I have changed the integration from dV to dP and it goes from P1 to P2. Okay? So, there is a minus sign altogether. So, what you are getting? You are getting nRT log of, if we integrate 1p cancels out, log of P2 by P1. Okay. So, now I have P2 V2 is equal to P1 by V1. Okay. So, what do I get my work done as? You see what I have done. I am writing again the same integral work done PdV from V1 to V2, PV is equal to nRT. So, I get V is equal to nRT over P dV is equal to minus nRT over P square dP. I am just taking the differentiation. So, minus nRT P by P square dP, and now I integrate from the initial value of the pressure to the final value of pressure, which I get P2 by P1, and now use this result. Now use this result, P2 by P1 is actually V1 by V2, nRT log V1 by V2. Okay? This is always equal to nRT, which is equal to the constant Ci I mentioned. So, you see, you just take care of this minus sign, you get nRT log V2 by V1. Okay? If you compare with the previous slide, this is precisely the result we obtained. So, you see, this result can be obtained in an alternative way. I did it only to give you a different mathematical procedure. So, this is all about isothermal processes. Okay? You should remember, when work done is positive, which means system absorbs heat, and when work done is negative, which means the contraction process, in which work done is negative and the system releases heat, and internal energy never changes because I am considering an ideal gas. In an ideal gas, internal energy is entirely a function of temperature T. So, let us proceed. We now have isochronic process. Volume is kept fixed. Okay? Let us go slowly. If volume kept fixed, temperature and pressure, they do change, and so does internal energy, because temperature changes means internal energy must change. Okay? But no work done, because again work done is PdV, and I have said in the beginning change in volume dV is equal to 0. So, now I ask the question whether the system absorbs it or it releases it. Okay? That will be determined by the change in internal energy. Again, as I told you, recall the first law, delta Q is equal to du plus delta W. This fellow is 0 in the present case. So, you see, internal energy dictates whether delta Q is positive or delta Q is negative. So, heat absorbed, that means increase in temperature. As soon as you know there is an increase in temperature, and which always implies pressure is also increases, because we know P is proportional to T if V is constant. Then internal energy increases, because temperature has increased, internal energy must increase. Now, if heat released, delta Q is negative, du is negative, internal energy decreases. So, again repeat, isochronic process, volume is kept fixed, no work done, you are going from P1 V T1 to P2 V T2. Since no work done, delta Q is entirely determined by du, heat absorbed, system temperature increases, which also means pressure also increases, and internal energy increases since temperature increases. In the reverse process, if delta U is negative or heat is released, that means delta Q is negative, then du will be negative, internal energy will decrease, temperature will go down, and so does the pressure. So, this is isochronic process. Now, we go to the next process, isobaric process. Isobaric process means pressure is kept constant. Okay? Here pressure is kept constant, volume and temperature they do change. Okay? As soon as you know that temperature change, there is a change in internal energy. Okay? This is your isobaric process, in which you go from P V1 T1 to P V2 T2. So, pressure is kept fixed. So, calculation of work done becomes very simple, and this is simply given by this. In going from this step to this step, we have simply used the fact that PV is equal to nRT. Initially, it was PV1 is equal to nRT1, finally, PV2 is equal to nRT2. So, this expression is very transparent. If I consider an isobaric expansion, so if you consider your isobaric process and try to show it in the PV diagram, you see pressure is constant, let us say this is some value, and volume goes from V1 to V2. So, this is your work done. This area under the curve is work done, and that is, this is V2, V1. So, you know area under this curve is P V2 minus V1, which I can write also in terms of temperature only. Okay. If there is an expansion, that means V2 I am going this way. If I go this way, V2 is greater than V1, which implies T2 is greater than T1. Again, if pressure is kept constant, volume is proportional to temperature, okay? Because PV is equal to nRT for an ideal gas, and you know that pressure is kept constant, volume is proportional to temperature. So, V2 greater than V1 implies T2 is greater than T1. So, work done is positive. There is a change in internal energy, which is also positive, because temperature has gone up. Internal energy being proportional to temperature for an ideal gas must also go up, and system absorbs it. Okay. So, delta Q is equal to du plus delta W. It so happens this fellow is positive, work done is positive, du is also positive. So, I must have delta Q positive, which means system absorbs heat. Okay. So, now we think of contraction. Contraction means, remember, your V2 is final value and V1 is the initial value. So, contraction process, if I draw in PV diagram, you are coming from V1 to V2. So, you see work done, definitely work done here, since V1 is greater than V2, work done is negative, change in internal energy is negative, and system releases heat, because in this first law du is negative, delta W is negative. So, delta Q is also negative. So far we have summarized three processes. First, isothermal. Isothermal, what is important about isothermal? Temperature is kept fixed, whereas pressure and volume change, satisfying the relation PV is equal to nRT, which I have denoted by a constant C sub I. Okay. Internal energy does not change, and you can calculate the work done, and you can find out very easily when work done is positive, system absorbs heat, and wherever work is done on the system which releases heat. Okay. This is isothermal, and then I gave you an alternative way of same derivation just to show you some mathematical trick. Finally, isochronic and isobaric processes. Isochronic process, volume is kept fixed, but temperature and pressure change, and so does internal energy, and hence you can calculate very easily the expression for the heat absorbed or released, which is simply given in terms of the change in internal energy. There is no work done in an isochronic process. Whereas in the isobaric process, pressure is constant, but volume temperature can change, but they change in such a way that V is proportional to temperature. That must happen because PV is equal to nRT, okay, pressure is kept constant. Now, here also internal energy changes, and you can talk about two processes. one is expansion and one is contraction. Here one has to be careful, you always be careful. Remember, V2 is my final volume, V1 is my initial volume, and I am going from PV1T1 to PV2T2. These three processes are unique in one sense, or they have something common in some sense. What is that? I have three thermodynamic variables: pressure, volume and temperature. In all these three processes I mentioned here, I see two of them are changing, one is kept fixed. Now I will go to the most complicated one, which is called the adiabatic process. In an adiabatic process, there is no heat exchange. So, I can write delta Q is 0. So, it will be an interplay between the internal energy and the work done. What is most important here, that pressure, temperature and volume, all the thermodynamic variables change. So, P1 V1 T1, P2 V2 T2. I am starting from P1 V1 T1, I am going to P2 V2 T2. Okay? In deriving the work done in an adiabatic process, I proved Cp minus Cv is equal to R for ideal gas. Throughout this discussion, we are considering n moles of ideal gas, for example, or n is equal to 1, you can set if you so wish. Cp minus Cv is equal to R, and the process is characterized by Pv gamma is equal to constant. It is not Pv is equal to constant. Pv is equal to constant is a characteristic of an isothermal process in which temperature is constant. Pv is equal to nRT for ideal gas. If temperature is constant, Pv must be equal to constant. But here temperature is not constant. Hence, we have a different equation describing my PV diagram, which is Pv gamma is equal to constant, where gamma is equal to Cp over Cv. So, in an isothermal process, Pi Vi is equal to Ci. For an adiabatic process, Pa Va to the power gamma is equal to Ca. Please remember, gamma is always greater than 1. Okay? Cp always exceeds Cv thanks to this relationship. Okay? So, now I can draw things in a PV diagram. I give you two curves. Okay? These two curves intersect at some point, which I am denoting by V0 and P0. I am asking the question, by looking at these two curves, can you tell me which one is isothermal and which one is adiabatic? Remember, one is characterized by the equation Pi Vi is equal to Ci, whereas the other, namely the adiabatic process, is characterized by this equation here. Okay? Now, you have to think a little bit, but I can tell by just looking at these two PV diagrams, this is adiabatic process, this is isothermal process. How do you do that? They intersect at the point P0, V0. You can immediately see that the curve which I denoted by adiabatic, okay, this is steeper, this is steeper. Okay. So, you should look at this slope. You can look at the slope and see which curve is steeper. Adiabatic is always steeper than the isothermal, which I am going to show in few lines in the coming slide. Okay. So, question is, I have two curves in the PV plane, they intersect at a point P0, V0. I am asking the question, which curve do you think represents an isothermal process and which represents an adiabatic process? I am saying this one, which has a steeper slope at the point of intersection, is representing an adiabatic process, the other one is an isothermal process. Let me give you a very quick proof of this thing. Please remember this picture in your mind. Okay? So, isothermal process, isothermal. In isothermal process, I have Pi Vi is equal to Ci, whereas in the adiabatic process, I have Pa Va raised to the power gamma is equal to Ca. Okay? Now, let us refer to isothermal process. Pi is equal to Ci by Vi. Let us calculate the slope in an isothermal process, del Vi, which is nothing but Ci by Vi square, but at the point V naught. What is V naught? Let us go to the previous slide, this point of intersection. I am calculating this slope here. Okay? So, this quantity, now thanks to this equation, I can write Ci as minus Pi Vi by Vi square at the point V naught. I got rid of the constant Ci completely, and I can find out what is the expression. I can immediately find out this is nothing but Pi Vi by Vi square. I cancel one of this, and this is getting at P naught V naught. So, the slope is given by P naught V naught. This is the slope of the isothermal curve at the point of intersection. Now, let us go to the adiabatic. Let us go to the adiabatic process. In an adiabatic process, on the other hand, I have that equation. Okay? Let me rewrite it. Is equal to Ca. I want to calculate what is del Pa del Va again at the point P naught V naught, point of intersection. If you calculate this, this turns out to be gamma Ca Va gamma plus 1. Now, what is Ca? Ca is Pa Va gamma, and remember I am calculating at P naught V naught. Here also it is better to mention that it is P naught V naught. Okay? So, if I do that, immediately one can calculate, I will not show all these steps, gamma P naught V naught. So, you compare these two. This is the slope of the isothermal curve, this is the slope of the adiabatic curve, where at the point of intersection, which is designated by the coordinates P naught and V naught. You see, this is two curves. So, whatever is steeper is adiabatic, whatever is not so steep is isothermal. So, slope of the adiabatic is gamma times, this is, I write it separately, gamma times P naught V naught, which is nothing but the slope of the isothermal. So, this is the question I posed in the last class. I gave you hints also that calculate the slope. Slope of the adiabatic at the point of intersection is gamma times more the slope of the isothermal. That is why I am saying that adiabatic curve is steeper than the isothermal curve. Now, we can ask the question that given two curves on the PV diagram, okay, let us say I know this is my adiabatic, this is my isothermal, this is my adiabatic, this is my isothermal. Let us call this point of intersection as O, which has coordinates P naught, V naught. Okay. Now, let us consider an expansion process. That means, from V naught I go to some V 2, which is here. Let us say this is my V 2. And also a contraction process. Start from V 0 and go to some V 1. So, this is your V 2, let us say this is your V 1, okay. This is your V 0, okay. Now, ask the question, if I consider an expansion process, work done is more in which process, adiabatic or isothermal, if I start from same V naught. Okay. Let me address this question. I have defined an expansion process, I have defined a contraction process, and work done will be more in which process? In both the cases, in adiabatic or in isothermal. The picture itself has the answer. Let us discuss this. Let us start by considering the expansion process starting from V naught to V 2, okay? And I have an adiabatic process and also an isothermal process. What is the work done in the adiabatic process? This is simply the area under this curve, okay? So, you can easily look at this area under the curve, and that is your work done. Now, what is the work done in an isothermal process? This will be this area plus this area. So, in this expansion process, you can see work done in the isothermal process is more. Okay. Whereas, if you look at the contraction process, you see your isothermal curves lies lower than the adiabatic curve. So, this is the work done in the isothermal process, whereas this is the work done in the adiabatic process, which includes the smaller part and also this bigger parts. So, in the contraction process, remember both the processes I am starting from V naught. So, you have to consider the area starting from here. Okay? So, contraction process on the other hand, adiabatic work is more. Work is more. Is more. Please note, in an expansion process, work done is positive, while in a contraction or compression process, work done is negative, which means work is being done on the system. So, when I say that work done is more in the adiabatic process, in a contraction from V0 to V1, I refer to the magnitude of the work. It means I need to do more work on the system in the adiabatic process. So, what we learnt in these two slides, that adiabatic curve is steeper. slope of the adiabatic curve is gamma times more the slope of the isothermal curve at the point of intersection. Please remember, gamma is greater than 1. What is the consequence? From the intersection point, which is at P naught phi naught, you consider an expansion up to a volume V2. Work done in the isothermal process is more in comparison to the work done in the adiabatic process, because isothermal process has this additional area. On the other hand, it is reverse if you consider contraction process, in which adiabatic curve lies above the isothermal curve and adiabatic work done is more, because you have to include this area, this small area also. This is what I wanted to say about two subtle issues about the adiabatic process. I repeat, it is the most complicated because you are changing all the thermodynamic variables you have at hand, namely pressure, volume and temperature. Now, we calculated the work done. Work done is of this form, which is nR T1 minus T2 gamma by 1. T2 is your final temperature, T1 is your initial temperature. That is how we have fixed our notation. If T1 is greater than T2, okay, that means you are going to a lower temperature, internal energy definitely will decrease, because it is a function of temperature rather proportional to temperature. Work done is positive. T2 is greater than T1, which means you are going to a higher temperature. Starting from the lower temperature, internal energy will increase and work done is negative. Well, remember here delta Q is 0, which tells me delta W, this is very important. I just wanted to show few more mathematical steps. Since we have this relation all through in an adiabatic process, we always have this relation satisfied. P1 V1 gamma is equal to P2 V2 gamma is equal to Ca. I can express this entire work done in terms of volume only. Ca carries the information about the pressure. So, this is the expression which you can also write in terms of Ca. This may be useful in our later discussions. So, this completes our recapitulation, thorough discussion of work done in different thermodynamic processes. Mathematics, I have not done this class because all these mathematical steps were done in the previous class, but the subtle issues which I did not consider in the previous lecture, I have unfolded them so that you understand these processes by heart. We need to use these processes in the definition of engine and refrigerator, to which I am going to proceed now. Okay. Before that, I have to bring in notion of reversibility. What do you mean by a reversible process? We have been talking about quasi-static process. So, whatever process we have used so far are quasi-static. Small changes, system is always in equilibrium, or at least I can assume within the time scale of experiment the system is in equilibrium. If it is an ideal gas, I can write PV is equal to A naught T. Furthermore, I will now assume that it is non-dissipative, no friction or viscosity. There is no dissipative force. Okay? So, I have already given these hints that you can have a forward process or a backward process. Once again, I draw a PV diagram. I do not care whether it is isotherm or whether it is adiabatic. I just draw a PV diagram. So, this is my volume and this is my PV diagram. I am going from, let us say, A to B. What do A and B imply? Those imply that initial values Pi, Vi, Ti, P1, V1, T1 or P2, V2, T2, which is B. Okay? So, this is my forward process, let us say. Okay? Forward process takes me to something P1, V1, T1 to P2 V2 T2. Okay. Now, if I revert the direction of arrow, what does it mean? I mean that I am going from P2 V2 T2 to P1 V1 T1. So, forward process means I am going from P1 V1 T1 to P2 V2 T2, whereas backward process implies the reverse. I am going from P2 V2 T2 to P1 V1 and T1. Okay. A reversible process means this forward and backward processes are completely equivalent. What does it mean? If in this process, let us say forward process, in the forward process I have delta Q heat supplied or heat released, delta W is the total work done on the system or by the system, delta U is the change in internal energy. If this represent my forward process, in the backward process I should have minus delta Q minus delta W minus delta U. Okay? That is what I mean when I say forward and backward processes are completely equivalent. If I go from A to B, delta Q is heat supplied or is extracted from the system, delta W is work done, net work done on the system or by the system, delta U is net change in the internal energy. In the reverse process, when I go from B to A, everything should be negative. Delta Q goes to minus delta Q. If I absorb a heat delta Q in the forward process, I must release an amount of heat which is minus delta Q in the reverse process. Similarly for work, similarly for internal energy. If internal energy change, net change is positive, an amount is delta U, in the reverse process it will decrease by an amount delta U, same amount. This is what I mean by forward and backward process, and in a reversible process these are equivalent in the following sense which I have elaborated here. Now, if you consider a finite process from A to B which I have drawn here, you can take any section of this. Let us say this is from C to D, a small part of the entire PV diagram. This small part should also be reversible. Okay? What do we mean by that? In this small part, again I have delta Q, delta W and delta U. If I do a reverse, so I can go from C to D or D to C. Okay? The same equivalence, that delta Q goes to minus delta Q, delta W goes to minus delta W and delta U goes to minus delta U in the backward process, which is here from C to D, holds true. Okay? So, what I mean to say here, if I have a reversible process, every small segment of this process must be reversible. So, this equivalence what I have said is valid. Obviously, it should be quasi-static, otherwise I cannot define internal energy, work done in the intermediate processes. My system should be at equilibrium at every instant of time. So, it is quasi-static, and secondly this connection, this equivalence I have presented here, okay, will hold true only I have no dissipative force, no friction, no viscosity, then I can have a reversible process. Okay. So, all the processes I will talk about so far it is quasi-static plus reversible okay, with an advantage. What is the advantage of reversible process? If I know the forward process, I know delta Q, delta W and delta U for a forward process. I know it for the backward process also. Similarly, if I pick up a small segment of the process as I have shown it here, CD, okay, in this small segment also, if I know the quantities for the forward process, I will immediately know the quantities for the reverse process. Okay. So, forward and backward process, or I call it sometimes forward and reverse process, they are equivalent, they have a connection. I know about the one process, I immediately get to know about other processes. So, the concept of reversibility is very, very important throughout thermodynamics, and it turns out to be very important in the next set, in which I am going to define engine and refrigerator. Okay. So, now brings in the concept of heat engine. Why thermodynamics is a very important subject? Okay. It is very important subject because of this possibility of constructing heat engines and reservoirs. Okay. If you go back to history, you will see entire industrial revolution started from steam engine. Okay. So, engines are very, very important because I need work, I need to extract work, and work I can get from heat engines. I need refrigerator in hot weather, and the principle of refrigerator works based on the laws of thermodynamics. So, what do we mean by engine? An engine, I will have a working substance. For example, I gave you the example of steam engine. Steam in steam engine is the working substance. But in our case, we have calculated work done from ideal gas in various thermodynamic processes. So, we will consider ideal gas. Okay. It works in a closed cycle. What does it mean? If I start from P, T, V, these are my initial thermodynamic variables. At the end of one cycle, I should come back to PVT, or rather this defines a cycle for me. I start from initial values of pressure, temperature and volume. My final value should also be the same P, T and V. This is a cycle. An engine goes in a closed cycle. That is obvious. It has to go in a closed cycle so that we can keep on getting work from the engine. But also what is obvious, that involves multiple thermodynamic processes. Why multiple? We have seen 4 thermodynamic processes. None of the processes which we have discussed so far can bring you back to same P, V and T. Okay? So, you involve multiple thermodynamic processes, then only you can come back to your initial thermodynamic variables. Someone talks about isothermal, temperature fixed, but pressure and volume will always change in the isothermal process. So, I must have some other process which you will soon see, an adiabatic process, to bring pressure and volume to an initial parameters. But not a single adiabatic, not a single isothermal will do the job for me. I need multiple processes. How many? We will soon see when we discuss about Carnot engines. So, I have a working substance. This working or the working goes in a closed cycle, that is multiple thermodynamic process. I start from PTV, I should come back to PTV. Works in a closed loop between 2 heat reservoirs. Okay. So, engine assumes the existence of 2 heat reservoirs. One is hot, which is at temperature T1, Another is cold, which is temperature T2. So, I write it T1 greater than T2. So, this working substance will work in a cycle between these two heat reservoirs with temperature T1 and T2. They are reservoirs, they are very weak. If you like, they have infinite heat capacity. How much heat you may extract from them, their temperature do not change. So, T1 and T2 are fixed. T1 and T2 are fixed. An engine absorbs the heat, which is amount Q1 from the hot reservoir, and it releases some heat, which is Q2 to the cold reservoir, and you know conservation of energy, it tells us W is equal to Q1 minus Q2. What about internal energy? Internal energy cannot change. I told you, I am coming back to the same state. Same thermodynamic state means same thermodynamic state of variables. So, initial temperature and final temperature after a closed loop, they are the same, and internal energy for an ideal gas is proportional to temperature. So, dU or change in internal energy is 0. So, we do not care about the internal energy here. Okay? So, what is the essence? I have a working substance which I choose to be ideal gas, works in a closed loop, okay, between two heat reservoirs. One is having temperature T1, other is having temperature T2. T1 is greater than T2, it absorbs heat from the hot reservoir, the amount is Q1, and releases some heat to the cold reservoir with lower temperature, okay, is Q2. So, work done by the system is W Q1 minus Q2. This is conservation of energy. But change in internal energy is 0 because initial temperature and final temperature happen to be the same. So, let us do it pictorially. So, let us say this is my hot reservoir T1, this is my cold reservoir T2, this is my working substance, and it goes in a cycle. Okay? It goes in a cycle means, again I am saying, initial value of thermodynamic parameters are PVT. After a closed loop, the value is again PVT, and it going over many cycles. Okay? So, it is the heat absorbed, which I show by this arrow, is Q1, heat released to this is Q2, okay, and then W is the work I can extract from the engine over a cycle, okay, is W, and conservation of energy tells me this one. So, heat absorbed in a closed cycle, one cycle is Q1, heat released to T2 again in a closed cycle is Q2, and work done is Q1 minus Q2. So, I am extracting some work from the engine, and this is the work done over one complete cycle. Now, one can define efficiency of an engine. Efficiency is defined in the following: work done by heat absorbed in a complete cycle. Okay? That is simply Q1 minus Q2 over Q1. So, this is the expression. This is the expression. So, what could be the maximum value of this? Okay? What is the maximum value of it? I can write is W by Q1. Maximum value, possible value, when I can set Q2 is equal to 0, okay, then eta will be 1. Now, it is a big question. So, you see that I make Q2 smaller and smaller, efficiency of the engine goes higher and higher. Okay. Question is, can I make Q2 disappear completely from the problem? So, system absorbs heat Q1 and converts it to work. Then the efficiency will be identity, and that is a fantastic situation. Amount of heat I supplied is entirely gets converted to the work done. Question is it possible? Construct an engine whose efficiency is perfectly 1. We will come to the answer to this question very shortly. So, this is engine. What is engine in a nutshell? It absorbs heat from a hot reservoir, releases heat to a cold reservoir, and rest of the amount Q1 minus Q2 is converted to work. At least engine provides us work at the cost of heat energy I supply to the engine. Now, one can operate the engine in reverse order, and that gives what we call the refrigerator. So, I should not call it heat refrigerator, I call it simply refrigerator. Okay. Hot reservoir and cold reservoir, I again have two reservoirs, one is hot, one is cold, and I am asking the question, what happens in a complete cycle? Okay. Heat absorbed from the cold reservoir Q2. Note, earlier in the case of engine, heat was absorbed from the hot reservoir which was having a temperature T1. Refrigerator does the other way around. I told you refrigerator works in a reverse way. So, heat absorbed from the cold reservoir is Q2. It is taking heat from the cold reservoir and released heat to the hot reservoir. So, it is releasing heat to the hot reservoir, and this is funny. So, it takes heat from the cold reservoir. So, cold reservoir, it takes heat and dumps it to the hot reservoir. Okay. Now, this is an abnormal process. Engine, it was fine. It was taking heat from the hot reservoir, releasing into the cold reservoir, and in the process it was giving us some work. Here, since it is the other way around, I have to do some work on the refrigerator. Okay. Please note, work done on the system. These are all in a complete cycle. In a complete cycle, work done on the system is W. So, one can define a coefficient of performance, heat absorbed by work done. Okay. So, heat absorbed from the cold reservoir, heat released to the hot reservoir. This difference with the heat engines one should bear in mind. Furthermore, this time I am not getting work out of the system, rather work is done on the system. Okay. Now, proceed. Again pictorially, if I draw it, this is my hot reservoir T1, this is my cold reservoir T2, this refrigerator fellow, again I will choose to be ideal gas if you like, it could be anything. Okay. Now, it absorbs heat from here, follow the arrows I have drawn, Q2 amount of heat it absorbs, Q1 amount of heat it dumps, and then Q1 should be equal to the work done on it Q2 plus W. This satisfies my conservation. Okay. I take Q2 amount of heat and dump it to this. Now, I have a coefficient of performance which I have defined, heat absorbed by work done. So, Q2 by Q1 minus Q2. What will be my purpose? I want to have W is equal to 0, ideal situation, ideal. I would like to have W is equal to 0. If W is equal to 0, you see phi tends to infinity. So, what I will do? I will extract heat from a cold reservoir and I will dump it to a hot reservoir, but no work is required. Okay? Or rather, I will keep on working in a closed cycle, I will keep on extracting heat from the cold reservoir and no work is necessary to be done on the system. If that ideal situation I can achieve, then W will be equal to 0 and phi will be infinity. So, in engine case, ideal situation, maximum value of eta was 1. We ask the question, can I have an engine which has efficiency unity? Similarly, here I leave with the question, can I construct a refrigerator whose coefficient of performance will be infinity? No work will be needed, it will extract heat from the cold reservoir and I will keep on continuing doing that in a cycle. Answer is both the cases, answer is no. Why no? That we will discuss in the next lecture when I introduce you to the second law of thermodynamics. In the process, I will tell you about two processes or two possible machines, one perpetual motion of first kind and secondly perpetual motion of second kind. We will show both are impossible, one because of the first law and other because of the second law. So, I stop the class here today.